It's a great pleasure to be at this workshop. I had a fantastic time. I sort of agreed to talk about optimization for machine learning, and the plan is to talk a little bit about data analysis in the Department of Energy. So I work at Argonne National Laboratory, which is about 150 miles northwest of here. And we have a big X-ray machine. It's a $200 billion X-ray machine that's being upgraded at the moment. And so there's some interesting challenges that I'll talk about. And then the main part of my talk is to talk a little bit about optimization. So my background is in optimization, developing algorithms for optimization problems. And I'll talk how some optimization paradigms have an impact in machine learning. I should say that most of this work, in fact almost all of this work, is not my own work. So you have to forgive me if I'm sort of blundering along. And then I'll come to some conclusions and extensions. Luckily, there will be a skip out at some point in this talk where you can sort of go and do something else. So here's sort of the motivation for why we should be interested in machine learning, or why one of the motivations. And this is that the light sources, like the advanced photon source at Argonne or SLAC at Stanford, they're experiencing what people have called, like Ian Foster have called this datanami. So the rates at which data is being produced is fast overtaking the rates at which computing is getting faster and bigger. And so looking here from the sort of 1950s to the 2010s, you have about a 12 order of magnitude increase in terms of compute power. But at the same time, you had an 18 order of magnitude increase over these 5 decades in terms of what light sources are producing in terms of data. And so sooner or later, you're going to overtake, and you're not going to be able to keep up. And so doing computing and computer science optimization, doing statistics for these light sources becomes very important. And I have one example that sort of highlights why this is important. But before going there, a colleague of mine at Argonne, Chris Jacobson, created this slide, which is sort of shows the increase in terms of compute power. So notice that on the axis here, you have that's a logarithmic scale. So the increase in terms of the current data rates or burst rates that you expect from some of these light sources. So the names down here are different beamlines at Argonne. So Argonne is the light source is this big circle, and every few hundred meters or so you have an exit that corresponds to a beamline. And they're all going to increase by 1 or maybe 2 orders of magnitude in terms of the rates, the data rates that they're expecting. And so people are now, for example, talking about using supercomputers like Myra to actually just do the data processing for the advanced photon source that's next to Argonne. That's the people at the advanced photon source who would like to do that. The people who own Myra don't want anything to do with these, with the scientists, because they like to run big simulations on their machine and they don't want to do the data analysis. So there's a bit of a conflict going on there. But there's lots of things that come up for mathematicians and statisticians. So there's these experiments, even though they all are conducted at the same facility, they all have a different mathematics that underlies them. So there's different experiments, different observations. Some of them are time dependent, some of them are stationary. You repeat lots of experiments, and there's lots of opportunity there for data analysis. In some cases, these experiments are multimodal. So, for example, you have transmission X-ray tomography, where you just do the normal X-ray transmission that you see when you go to the doctor and get your hand X-rayed. But you also have fluorescence, where photons excite photons inside the object, and they scatter off to the side, and you have a detector that actually tells you something about the kinds of elements that you detected along the way on the path through the object. And then colleagues of mine are actually looking at new experimental designs. So traditionally, when you're scanning an object, you have your X-ray beam, and you slowly move the object through this X-ray beam to scan and basically get your pixelated picture of that object that you're interested in. It's often much more effective to actually do some spiral scans or something really bizarre that gives you a much better way of getting the object. So there's new experimental designs, but also using less exposure to these X-rays when you're detecting the object. So the data is becoming less regular, the reconstruction is becoming more complex, and there's this hodgepodge of math, computer science, statistics that you can throw at these problems. So here's one problem that I looked at, which was learning cell identification from spectral data. So what you see on these images are the maps of potassium, manganese, iron, and zinc, top left to bottom right. And you're supposed to find where the cells are and identify different kinds of cells in these images. So these are cells that images that people have taken at the Advanced Photon Source. The way we approached this was to sort of first do a kind of data reduction where we reduce this high-dimensional, the spectral data using a non-negative matrix factorization, where we decompose it effectively into maps of elements and then multipliers of these maps of elements. In practice, what you want to do is you also repeat this analysis possibly hundreds of times and eventually identify cancerous cells and so on. We didn't go there. So here's sort of the raw data on the left. In the middle, you see where we identified the cells, and then on the right, you classify the cells into different classes. And this is sort of semi-supervised learning, where we're given an idea of what content to expect in a typical cell. So these are red blood cells, and I think there are yeast cells. The green ones are yeast cells. Typically, how this had been done before we started this work at the Advanced Photon Source was that a lucky postdoc would be given the picture on the left, and he would be told to mark the potential location of the cells in the picture, and then you would try to do some data fitting to test whether those were really cells. Now, this is something that doesn't really work if the Advanced Photon Source increases by a factor 10, because you're not going to hire 10 times as many postdocs once the upgrade is completed. So there's lots of opportunities here. Sorry?
You shouldn't tell the people in this room that you're not going to hire as many postdocs.
No, sorry. We are going to hire lots of postdocs, but they're going to do smart things with machine learning instead of stupid things where they mark out little cells in pictures. So we want people who do machine learning. Okay. So after the sort of semi-commercial here for Argonne and why we're interested in machine learning, I'll talk a little bit about optimization for machine learning. And so I came across this book, which sort of has almost the same title as my talk, Optimization for Machine Learning, by these three guys, including Steve Wright. And this is really a great book. So there's lots of things in there that tell you about optimization and the impact it has had on machine learning. So it talks about convexity, for example, and one of the things it talks about is sparsity-inducing norms, and this is one of the things that I'll concentrate on later. And then it goes through the standard sort of optimization terminology, really non-smooth optimization, gradient, subgradient methods, and proximal methods. So those are very classical ideas. There's a nice paper in there by Jacek Gonce where he looks at interior point methods and Newton methods, arguing that maybe you need more than just first-order methods for certain problems. There's work on cutting plane methods. There's some interesting papers on augmented Lagrangian methods and its connection to ADMM. And then later papers are on uncertainty and robust optimization. So this is also something that I'll talk about in this talk. And then lastly, there's something about invariance and inverse covariance selection. Now, at this point, I should give a fair warning that Argonne made me put in here, namely that I made zero contribution to this fantastic book. So I was not a co-author. I didn't even referee the paper. I just read part of this book. And worse, until yesterday, I had no clue about optimization for machine learning. So you're really in for a treat here. I finished my slides at about 7:30 this morning. I didn't work through the night, so I slept. But one thing I wanted to do also was there was a really great talk by Moritz Hart from UC Berkeley that he gave at the Informs Optimization Conference. And this was a great talk for two reasons. One, it talked about machine learning, but two, it sort of had a very challenging title for somebody giving a talk at an optimization conference to call it non-optimization. And he sort of identified these four lens of learning, which is a good way of a warning, I think, that is good for optimizers, so not maybe for you, but for people who optimizers in the room to heed when you're looking at applying optimization methods to machine learning. And so he sort of talked about this first lender, which is convexico, where in many cases you have this really nice regular Hessian matrix, often the identity matrix, and methods converge very well. That may not happen in all the cases. And so Jacek Gonsia has some very nice examples where maybe you need to look at other things. The sort of gradientina is the sort of idea that somehow the steepest descent or gradient method somehow stochastic gradient method somehow regularizes your method or your solution. And of course, this is sort of really the warning for the optimizers and the warning for you in terms of what you should take away from my talk. So I'm not going to give you solutions. I'm not going to give you the panacea of how optimization is going to save machine learning. Sort of this search for sort of some overarching optimization goal that if we only knew this fantastic optimization problem, we would solve it and all machine learning problems would be solved forever. That's sort of maybe never happening, though some of the tools that we're using may be helpful in some small cases. And so what Moritz mainly said was, in many cases you're in messy land, it works, and if it works. And so at this point, if you're not happy with my talk, you're welcome to go to this website here, and you're welcome to sort of follow Moritz's talk, which might be much more interesting than mine. Okay. Right, so now we'll get to sort of the meat of how optimization has impacted machine learning, and I've split this into two areas that I've been involved at. I've contributed to on the optimization side, though not on the machine learning side, which is the mixed integer optimization and then robust optimization. And so first I'll talk about mixed integer optimization a little bit. So a mixed integer nonlinear program, mixed integer nonlinear optimization problem is an optimization problem where you minimize some nonlinear objective subject to a set of nonlinear constraints, and there could be some other constraints that are denoted by x here, which could be mostly linear constraints, for example. And then you have these integer constraints. So some of your variables, a subset of your variables has to be integer at a solution. And so this corresponds to this picture on the right there, where you sort of see a feasible set. That's the blue region where you have two linear hyperplanes that limit where you can choose your variables from. And the red points correspond to the integer lattice. So your solution has to be one of those integer points. And you can see immediately that if you just minimize a function over this blue set here, then the solution might lie at a point out here or out here, for example, if it's a linear function that's not at an integer point. So you need to do something else. And what people typically do is some kind of branch and cut approach where you create these trees that I've sort of illustrated there on the right, where you keep solving nonlinear optimization problems or linear optimization problems, linear approximations, and you keep branching on variables until you eventually get to an integer point. And that's kind of related to finding, in a sense, the convex hull of these integer points. So the green region here is the convex hull. So once you have the convex hull of an mixed integer optimization problem, it's very easy to solve it. You just minimize your linear objective over this convex hull, and you're guaranteed to find an integer point. So these problems in general are NP hard, that was shown in '78, and worse, Jaroslav showed 5 years earlier that they're actually undecidable. So there are some very simple two-dimensional quadratic mixed integer optimization problems where no computing machine can decide whether you found a solution or not. And it's got to do with the directions of negative curvature that you can sort of follow off to infinity, and you don't know whether there's going to be another integer point that intersects these negative curvature directions. So the first problem that I want to tell you about that uses mixed integer nonlinear programming is this problem by a bunch of optimizers who are at IBM. So Leo Horish is one of them. That's the colleague that I know. And they're looking at optimal symbolic regression. And so the idea here is that if you're not given the symbolic, the functional forms of a regression problem, then can you find this functional form somehow? And so you're trying to find a symbolic mathematical expression that explains some dependent variables in terms of independent variables, without actually assuming that you know what the functional form is. So it's a bit like least squares, but you don't know that it's a linear function. It could be any functional form that you put in there. And they're looking at problems where they look for the simplest functional form because they assume that's presumably, using something like Occam's razor, that's the one that nature has selected. So that's your objective, is trying to find the easiest or simplest form. You have constraints on the grammar. That means what kind of forms you can put into your expressions. You eventually want to match the data, so you have some observations that you want to match, and selecting this best possible expression gives you a binary optimization problem. And you can model these mathematical expressions using things like a directed acyclic graph. So here's a little bit of a side tour to what these graphs look like. Down here at the bottom, we have the expression tree of this nonlinear function. It's a very simple nonlinear function just of two variables. So the way they're constructed is you put your independent variables as leaves at the bottom, and then you're creating nodes whenever you have compositions of these functions. So log x2, for example, is created here, and then you multiply it with x1 in this next node, and you pass it up to the top, where you add x2 cubed to it to obtain the expression, the nonlinear expression f of x. So this is something that's called a factorable function. If you can put your function into this form where it's either made up of unary operations, which just depend on one variable, or binary operations, which depend on two variables, then you call a function factorable. And you can have any combinations of functions, any combinations of operators, but it excludes certain things, such as black box functions or integrals, for example, which you can't always write in this explicit form. And this technology forms the basis really of automatic differentiation. So ask Alex Poten. He's got a great paper in SIAM Review on this, and also for global optimization of non-convex functions. And so the idea that the guys from IBM were pursuing was, well, what if we don't actually know the functional form that we're after? Can we somehow find an optimization problem that puts this tree together? So we're wanting to build these trees, these expression trees, out of data that we have observed. And so what you can imagine is that you stick a tree together, and then you put your data, your independent variables at the bottom, you figure out what comes out at the top, and you look at the mismatch, the data mismatch. So it's very much like a sort of deep neural network. It's got a very similar flavor to that. And they did this, and there's two formulations of this, and I think the second formulation is better, where they form this super tree. So this is a tree that contains all possible trees that they want to consider. They use binary variables then to switch parts of the tree on and off, and they use continuous variables to propagate basically data through the tree that gives them then a data mismatch that they want to minimize. And in their example, they're minimizing the complexity. That's the number of binary variables that are switched to one. So the number of expressions that they're using, subject to a bound on the data mismatch. And then depending on how much noise you have in your problem, you get different, you recover different forms of the correct answer. So they tried this out on two examples, and I'm just listing one here. This is Kepler's law on planetary motion. And they get some data from NASA on planets in other solar systems that have been observed. And they built a tree of depth 3. So that's a very shallow tree if you think about it in terms of machine learning. But they're able to really match the correct answer, which is given down here, to sort of a reasonable amount of accuracy, right? M is the smaller the planet, big M is the sun that the small planet is orbiting. You're interested in this D, which is the major semi-axis. and tau is the period, and I forgot what c was here. It's not the speed of light, I don't think. But you get to something like the correct answer with these expression trees, and this is you're recovering, in a sense, you're recovering a formula without actually knowing what the formula looked like, and you had all sorts of expressions that you could have selected there, and you're recovering something to relatively good accuracy. And then as the noise increases, you can sort of make an argument that what you're recovering is still accurate to some extent. So you're taking terms out and do some kind of asymptotic analysis or so. The second instance of where people have used mixed integer programming in machine learning is sort of much closer to machine learning, I think, and this is in deep neural networks. And so Matteo Fischetti and one of his students looked at the model of a deep neural network as a mixed integer program. So in particular, and I should say this picture is taken from a web page, they model the maximization function, this activation function, using binary variables. I'll show you in a moment what this model looks like. And then you can model the output of your deep neural network in terms of the inputs, and you can solve you can solve deep neural networks of moderate size. So it's not going to be big problems that you can solve. Now this should sound a little bit, and I hope some people are looking a little bit puzzled in the audience, because this is not really a good idea if you want to train a deep neural network, because a mixed integer problem is NP hard, it's a difficult problem. Training a neural network, if you just want to evaluate it, you just propagate variables forward. That's a much, much cheaper way of evaluating that deep neural network than to solve a mixed integer problem. So this would be a daft idea for solving, for trying to train a deep neural network, because it's far too cumbersome and expensive to evaluate. But you can sort of use it to build adversarial advantages, examples that fool deep neural networks. So you can build it to design examples that will then fool a deep neural network. And so that's what they effectively did. So I'll tell you a little bit what this model looks like. So they assumed that they had a neural network with k+1 layers, where 0 is the input layer and k is the output layer. And they have a given number of nodes, nk nodes per unit, per layer. And on each layer, they call a unit. That's effectively the max function here. So they have the variable that comes out of that max function is then basically the output of that unit that operates there. And so here's this activation function is written here. So we assume now that the weights are already given. So we've trained the neural network. It's all the weights are given. So the bias and the weights are given. And I just want to model now the max function using integer optimization. And so this is not something that's terribly deep, but it's called an implication constraint. So you can model this max function just by the following implication here. You introduce one additional variable s, which is your slack variable, and you have that both x and s have to be non-negative. And then you have an additional binary variable 0, that's 0, 1, that switches these variables on and off. So if z is equal to 1, then you set x to 0. So you add an upper bound of x, that's 0, a lower bound of 0. So if z equals 1, x is 0. And if z equals 0, then you set s equals 0. And then the output must be x. And so you can easily see that that's exactly what you're getting out of here. So if this term here, for example, is negative, if w transpose y plus b is negative, then you must choose s. And so s has to be greater or equal to 0, which means x is 0, and you're choosing that. There's an alternative. You can also do this with complementarity constraints, but these problems are a little bit harder to solve in practice. So it's actually better to do it in this way. And you can also model the maximum pooling problem, where you have a range of variables and you're looking at the maximum of the range of these variables. And you do that by just introducing, again, t binary variables, one for each of these expressions that you have in your maximization, and then a special ordered set of type 1 constraint, which just says that you have to select exactly one of these t variables to be 1, and all others have to be 0. So that's a very simple linear constraint. OK, so with this, you can then write the output of your deep neural network as a mixed integer optimization problem. And so the thing that you do now is you write this activation function now in terms of this, these implication constraints. And down in a moment, I'll tell you how to model those. And then for a given input x0 here, this would just propagate through the system. And you could measure the output, for example, at the top of the variable k. But the interesting thing now is that you can put a range here. You can put lower and upper bounds on these input variables, and that allows you to find nearby examples from your training set that you can then force to fool your deep neural network. And so just to say how you can model this implication constraint, you can do this algebraically. Instead of using implications, you can use these algebraic equations just to see that if z is equal to 1, then mx is some big positive number. X will be less than or equal to 0 if z is equal to 1. And if z is equal to 0, then x is unrestricted and s will be equal to 0. ms is another big positive number. And so the idea then is you fix the weights in this problem. This is now a well-defined mixed integer linear optimization problem. And then you're looking for the smallest perturbation, for example, of your input data that produces something in the output that's undesirable for the deep neural network. And you can have bounds on intermediate, you can have bounds on the final layer, and you can add objective functions here as well. And so Matteo did this for the digit classification. They wrote this as a mixed integer problem. And they were interested in actually misclassifying all possible digits from a training set. So they looked at examples where they wanted to misclassify a 0 as 5, 1 as 6, 2 as 7, and so on. And they required that the activation of a wrong digit was at least 20% above that of all the other digits. Again, that's something that you can write as a linear constraint in this optimization problem. One of the things you need in order to solve this efficiently, and you can read this in their paper, you need tight bounds on these upper bounds mx and ms that set the activation function to 0 in the right way. And getting those tight bounds there's a simple trick that they use. They propagate these bounds through the deep neural network up to the layer where they're interested in these bounds. And so they solve a number of linear programs offline ahead of time in order to get the tightest possible bounds. And if you do that, then you can find adversarial examples for sort of deep neural networks. I don't know if they're called deep, with sort of up to 5 hidden layers where there's 20 and 10 nodes on each layer. And you can solve these problems in sort of 180 seconds, so 3 minutes of CPU time, using state-of-the-art mixed integer linear solvers such as Cplix, for example. And down here you see the digits 5, 6, 7, and 8. So those of you who are paying attention. So this is what the digits look like once they've been through Matteo's falsification mixed integer problem. Okay, the last mixed integer sort of optimization application in machine learning that I wanted to talk about is support vector machines, and in particular sparse support vector machines. So here's just a recap of what a support vector machine is. We are given data that consists of features x, j, or xi, and labels yi that are either -1 or 1. And the optimization problem that we typically solve then is we're trying to find this separating hyperplane that's described by W and B that maximizes the separation between these two sets of points that we have. And you can write this problem as just a quadratic optimization problem. So this is just a continuous quadratic optimization problem. You don't actually need the one norm here because psi is non-negative, so you're never going to sum up negative values there. So that's a nice quadratic optimization problem. Your Hessian is the identity matrix. And this problem is well studied in the literature. Now, what we're interested in is to find solutions W where we have as few Wi's that are non-zero as possible, because people believe that that's a good way of finding robust classifiers, for example. And I'll get back to that later on. So the idea then is to somehow minimize the cardinality also of this weight vector W. So that zero norm is just the numbers of non-zeros of W, and of course that's not a norm. So if you're a student, please don't write down that this is a norm. If you're a professor, it doesn't matter. Cool, so this problem has been studied by a number of people. So these guys looked at the zero norm penalty on W and solved this as a mixed integer nonlinear problem. So it's difficult to minimize a problem where you have this zero norm as an objective. So you want to reformulate it using binary variables. And so this is this model down here, which uses conic constraints. So let me explain how you get from the zero norm up here to this problem down here. You introduce a binary variable, zj, that's 1 if and only if wj is positive and it's 0 otherwise. So wj counts the number of non-zeros, sorry, z counts the number of non-zeros in w. So then, whoa, where am I going? There we go, sorry about that. So E transposed or 1 transpose Z is just the number of non-zeros in W. So that's exactly the term, the W0 term up there. And then these two constraints down here ensure that, first of all, Z is a binary variable. So a W is either 0 or positive. That's going to be taken care of by Zj. And then this constraint down here models the fact that if Zj is equal to 0, then Wj is also equal to 0, right? Zj is 0, Wj squared must be 0, so Wj must be 0. On the other hand, if Zj is equal to 1, then effectively what we're saying is that Uj is now an upper bound on Wj squared. And if you look at the objective here, I'm summing up the u's up here. And so the u, if the z is equal to 1, then u is equal to Wj squared. And it can't be any bigger than Wj squared because I'm minimizing u here. So that's pushing it down, which means there can't be any slack. And that's the same reason why if Wj is 0, then z will also be 0, because if z was 1, then I have a penalty on this z here, and I would push it down to 0. So these two problems are entirely equivalent. That's a nice formulation. This is called a conic mixed integer problem. Effectively, this formulation here has something to do with the perspective of this function here. So this is the quadratic, the x squared function here. And here now the binary variable is y is equal to 0 here and y is equal to 1 there. So as you go from the binary from 0 to 1, you're tracing out these rays, and that corresponds to the convex hull that you're tracing out there. Now this formulation, unfortunately, if you just pass this to your standard mixed integer nonlinear solver, they will usually barf at this because at some point, because this formulation violates a constraint qualification, so it violates a sort of necessary condition for these or sufficient condition for these algorithms to converge. So in some cases they may not work, the nonlinear solvers, so there's a weaker big M formulation, but that turns out to make the relaxation really weak. You no longer have the convex hull, you have something that's bigger than the convex hull, and so you're spending much, much more time searching the branch and boundary, and so this is not really practical. So Noam Goldberg came up with an equivalent reformulation that actually reformulates this conic constraint as as this sort of this 2-norm constraint here, and then he applied a conic solver. So he had an active set method, a conic active set method that he wrote that he could apply to this problem and solve problems of second-order cone constraints. He didn't actually minimize the number of ZJs in his objective. He added a sort of regularization to it, an upper bound on the number of WJs that were non-zero. And he solved a relaxation, so he wasn't interested in finding 0-1 solutions. And so what he observed was, first of all, that I think his algorithm is this CQ SVM, that it gets reasonably good classification accuracy here on the y-axis, so that's reasonably good, even for small values of the 0 norm of W. And then as he increases R, he's kind of tracing out the sort of the right number of non-zeros in W. It sort of almost lies on this R axis. So he traces out almost the right number of non-zeros in W, which is kind of a nice result. There's an alternative formulation which is due to Martine Labé and some of her colleagues from Holland. They looked at a mixed integer linear support vector machine. So they're just minimizing the classification error, psi, that's the slack, subject to, again, an upper bound on the number of non-zeros in your separating hyperplane. And so for this budget constraint, they again count the number of non-zeros with this ZJ. They now have bounds on lower and upper bounds on these WJ. And in fact, some of the best results they get if they set the lower and upper bounds to 1. And they can solve this problem. And this is a much easier problem to solve because it's a mixed integer linear problem. The previous one was a problem that had these conic constraints. They're still convex constraints, but they're much harder to solve numerically. This is a much easier problem to solve. You can warm start these problems and solve these problems to global optimality quite easily. So for support vector machines, this is, if you're looking for sparse support vector machines, there's a way of doing this using mixed integer programming. Okay, so last couple of minutes or so, I talk a little bit about nonlinear robust optimization. And so the interesting part about robust optimization is that it's related to optimization under uncertainty, and it gives some insight as to why some of the regularization techniques that people used in machine learning might be the right way to proceed. And so here we're looking at optimization problems where we're minimizing, again, a nonlinear objective subject to this constraint that now has to hold for all u in U. And U is not a finite set anymore. It could be an interval, for example, or a region, a bounded region. And so this set of uncertain parameters is usually a closed convex set. But that means that this constraint that we have, this constraint here is now a semi-infinite constraint because I have an infinite number of indices or parameters for which this constraint has to hold. And it's kind of interesting if you look at small examples, then even though the constraint here in this example is a linear constraint in X that has to hold for all U, if you trace this constraint out, you actually get this nonlinear effect here. Now, robust linear constraints, and to some extent conic constraints, are easy to solve. So here's your 1 minute or so introduction into robust constraints. So imagine, and this is due to Ben Tal and Mirovsky and other people, imagine that your robust constraint is just this linear constraint where A, so this vector A here is uncertain. It belongs to this uncertainty set, which is also described by a set of affine or linear inequalities here. Then saying that this constraint holds for all A that are in this set is the same as saying that if I minimize this function here over all A and U, then I'm greater or equal to 0. Right? That's like saying if we want to find, and now I can apply duality to this optimization problem here. So I just write down the Lagrangian, introduce Lagrange multipliers lambda corresponding to these constraints down here, B transpose A greater or equal to C. And if I write down the dual problem, then it turns out that I can eliminate the variables A now from this dual problem. So this dual problem now is just an optimization problem, maximization problem, just in the dual variables lambda. And this is just duality for linear programming. And now you just observe that, well, if the maximum of this function over the set down here is greater or equal to 0, if and only if I can find a feasible point for which this assertion holds. And so I've now replaced this semi-infinite constraint up here that had to hold for all A that lie in this affine set here. So this is a bounded region. I've replaced this by something where there's nothing red anymore. And so this is a finite set of inequalities. So red has disappeared. Red was the thing that caused us to have semi-infinite constraints. The same tractable extensions hold for other sets of constraints where you have robust constraints and uncertainty sets. If they are in general polyhedral, you get a linear program. I just showed you this case. You can have ellipsoidal uncertainty sets. So these will correspond to maybe uncertainties in terms of normal distributions. And you can have even conic constraints and get similar results. And so Karamaris and Bertsimas looked at problems, sort of robust optimization for support vector machines. And in particular, they looked at having a location error ui. So the observations that you make xi is the true observation perturbed by some ui. And this ui is unknown. That's some unknown error. But you're assuming that this lies, for example, in this ellipsoidal uncertainty set. And then using similar arguments to the one that you just saw for linear programming, you can show that this semi-infinite constraint, which is part of your, which would be part of your robust support vector machine training problem, where this UI comes from this ellipsoidal set here, can be rewritten now in terms of this deterministic constraint. So what you've added here is you've added a 2-norm constraint that corresponds to the square root of sigma. Sigma is a diagonal scaling matrix, for example, certainly positive definite, that you can add to it. And so this is really nice. This is now a second-order cone constraint. There's algorithms, polynomial time algorithms, interior point methods that can solve these problems. And so this generalizes, and I don't want to say too much about it, I'm out of time already. This generalizes to much more general constraints. So you can have an uncertainty set U here, where you have some distributed uncertainty with a parameter D, and then what you end up having in your deterministic equivalent is this dual norm here that pops up here. And that's exactly what you saw on the previous slide. The dual norm of the 2-norm is the 2-norm itself. And so that sort of explains this. And there's a nice argument in this paper by these guys that shows that regularized classifiers are often more robust because they satisfy this worst case principle. And in fact, you can provide even probabilistic interpretations of these ideas if you move to chance constraints, which is a different concept in optimization under uncertainty. Okay, so to conclude, I'm sorry I'm over time. I've showed you a little bit about mixed integer optimization and how that impacts machine learning in sort of 3 areas: symbolic regression, where you're manipulating the symbolic parts of your tree, mixed integer problems for deep neural networks, and support vector machines with L0 norm regularizers. And then I showed a little bit about robust optimization for machine learning. And so there's lots of extensions and challenges, I think, where optimization can play a role. I've just written 2 here, but in terms of using optimization technology, I think there's sort of interesting niche markets, but ultimately it's not the panacea. So this is a big problem that requires more technology than just optimization. Thank you.